A black hole should be impossible. According to the laws of quantum mechanics, information, the precise configuration of every particle, every field, every quantum state, can never be destroyed. Yet a black hole seems to do exactly that. It swallows matter, light, and the full informational signature of everything that falls within it, then radiates away its mass as featureless heat until nothing remains. The universe, in theory, should remember. A black hole forgets. Einstein's general relativity predicts that when enough mass collapses under its own gravity, space-time itself folds inward, forming a singularity, a point where density becomes infinite and known physics dissolves. Around it forms the event horizon, a boundary from which no signal can escape. To relativity, the story ends there. The information is trapped beyond reach. But quantum theory refuses that ending. It insists that every interaction, however extreme, must preserve information, even if it becomes impossibly scrambled. The contradiction is absolute. Stephen Hawking's calculations in the 1970s deepened this fracture. He showed that black holes emit faint thermal radiation, Hawking radiation, causing them to slowly evaporate. Yet that radiation carries no trace of the detailed structure that fell in. Once the black hole vanishes, the information seems gone forever. The laws of physics, which rely on reversibility, collapse with it. What evaporates isn't just matter, it's meaning itself. The paradox cuts to the heart of reality's coherence. If black holes truly erase information, then quantum mechanics, the most accurate framework ever tested, fails. If information survives, then space-time, as Einstein described it, is incomplete. Either way, something fundamental, perhaps even our concept of reality, must be rewritten. The universe cannot both remember and forget, yet it does. To understand what the black hole seems to destroy, we have to trace how it forms. Imagine a massive star exhausting its nuclear fuel. With fusion halted, gravity gains the upper hand. The star's core collapses inward, compressing matter past the point where atoms, nuclei, even quarks can resist. Density rises without limit, and space-time itself curves so steeply that escape becomes impossible. What remains is not an object in space, but a region of space, a gravitational well so deep that even light cannot climb out. From the outside, all that defines the black hole are three numbers: mass, charge, and spin. This is the essence of the no-hair theorem. Two black holes formed from completely different histories, a collapsing sun or a cloud of antimatter, are indistinguishable if those three quantities match. Every other detail, every bit of quantum structure seems to vanish behind the horizon. Information, once distinct, is erased from the universe's observable record. But quantum mechanics forbids such erasure. In quantum theory, the wave function, the mathematical description of all possible states, evolves in a way that is perfectly reversible. The universe may disguise information, but it cannot delete it. This principle, known as unitarity, ensures that from any present state, the past could in principle be reconstructed. A black hole violates that promise. When it hides data behind an event horizon and later evaporates into random radiation, the link between past and future breaks. So when a black hole consumes, the universe hesitates. Does it follow Einstein's smooth geometry and allow disappearance, or obey quantum law and preserve the trace of every fallen particle? One framework describes space curving, the other describes probabilities conserving. Both cannot be true in the same way, yet the cosmos behaves as if they are. A hole that devours matter is strange enough. One that devours logic is far stranger. Hawking's discovery began as a thought experiment, a confrontation between Einstein's smooth spacetime and the restless fabric of quantum fields. Even in the emptiness around a black hole, the vacuum isn't truly empty. Quantum theory tells us that pairs of virtual particles, one matter, one antimatter, constantly flicker into existence, borrowing energy from nothing for brief instants before annihilating each other back into nothingness. Near the event horizon, this delicate dance breaks symmetry. If a pair appears right at the edge, gravity can separate them. One particle falls inward, while the other escapes before annihilation. To an outside observer, that escaping particle looks like real radiation emitted by the black hole. Energy conservation demands balance. The particle that fell in carries negative energy relative to the outside world, effectively reducing the black hole's mass. Over immense timescales, this process causes the black hole to evaporate. Hawking radiation is pure and thermal, perfectly random, with no imprint of what the black hole once consumed. No pattern, no signature, no hidden message survives. Every photon it emits erases structure, smoothing complexity into featureless heat. This was the paradox's cruelest twist. Hawking's mathematics obeyed both quantum field theory and general relativity, yet the result defied both. Information, by every physical law, should remain, and yet the mathematics said it vanishes into entropy. If this radiation truly carries no information, then the universe's most precise rule, that the quantum wave function evolves reversibly, collapses. Time itself would no longer be symmetrical. The future could not, even in principle, unfold back into its past. The black hole does not explode, nor collapse, nor fade. It dissolves meaning into silence. A perfect object that unbuilds perfection itself. A black hole that evaporates should, by the logic of Hawking radiation, erase its own history. Each burst of energy that escapes is random, uncorrelated, devoid of any hint of what once fell inside. A billion tons of star matter, a photon of ancient starlight, a drifting atom, all end the same way, dissolved into anonymous heat. If this process is real, the universe commits an irreversible act of forgetting. In physics, that word, irreversible, is almost forbidden. The laws that govern particles are time-symmetric. If you reversed every motion, every collision, every vibration, the equations would still hold true. Information, therefore, is the thread that makes time intelligible. It guarantees that the future can, in principle, be unraveled into the past. A universe that forgets would be a universe that violates its own logic, a cosmos capable of producing events that have no definable origin. Hawking's result was not just unsettling, it was mathematically intolerable. If black holes truly destroy information, then quantum mechanics, a framework confirmed to 14 decimal places, must fail in its most sacred rule, unitarity. The total probability of all possible outcomes must always sum to 1. But when information vanishes, the sum becomes less than 1, an invisible deficit in reality's bookkeeping. Something is lost, not merely hidden. Physicists searched desperately for an escape. Some proposed that the information remains trapped at the singularity, inaccessible but not destroyed. Others suggested it escapes with the radiation in forms too subtle for current mathematics to see. Both options demanded that space-time itself, that smooth, continuous fabric Einstein described, must somehow store or encode quantum data. Space would have to remember. But if the universe remembers everything, it must do so through an architecture far stranger than geometry. Information cannot drift unanchored. It needs a substrate, a pattern, a place to exist. What if that place is not inside the black hole at all, but spread along its surface, encoded on the horizon like data on a cosmic screen? The idea seems absurd, yet it may be the only way the universe can both forget and remember, without contradiction. The first hint that the information might not vanish into the black hole's center came from an unexpected place: thermodynamics. In the 1970s, Jacob Bekenstein noticed something odd. When an object falls into a black hole, the total entropy of the universe, its measure of disorder or information loss, should increase. But where does that entropy reside? A singularity, a dimensionless point, cannot hold it. Bekenstein proposed that the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This was a radical reversal. In every ordinary system, information scales with volume. The more space you have, the more microscopic configurations you can store. But a black hole, the most extreme object in nature, seems to invert this rule. Its informational capacity depends only on its surface.
The event horizon, that invisible boundary where gravity traps light, might not just mark the point of no return, it could encode the quantum data of everything that falls in, like a perfect two-dimensional ledger of three-dimensional events. If true, then nothing inside the black hole is truly lost. Every particle, every photon, every quantum fluctuation would leave an imprint on the horizon, subtly altering its microscopic state.
From afar, the black hole appears simple, defined only by mass, charge, and spin. But beneath that apparent simplicity lies an astronomical number of possible horizon configurations, each corresponding to a unique history. The surface hides the story of the interior. This principle became known as the holographic hypothesis, the idea that the information describing a volume of space can be fully represented on its boundary. A black hole, then, acts as nature's proof, a cosmic projector showing that the universe itself might be holographic. What we perceive as depth, interior, and continuity could be the unfolding of data painted on the edges of reality. If information truly lives on the horizon, then no paradox remains. The black hole never forgets. It only translates, converting the chaos of collapse into a silent code along its surface. What looked like destruction may be the universe's most sophisticated act of preservation, a memory written on the border of nothingness. If a black hole's event horizon can store the full information of everything that falls within it, then perhaps the same principle applies to the universe itself. In 1997, physicist Juan Maldacena proposed a revolutionary idea that crystallized this possibility: the ADS-CFT correspondence, a precise mathematical duality showing that a universe with gravity inside a region of space could be perfectly described by a quantum field theory living on that region's boundary. In other words, a higher dimensional world with gravity might be fully equivalent to a lower dimensional one without it. This was not metaphor. It was a literal identity between two descriptions of reality: one bulk, one boundary. The holographic principle, once a poetic conjecture born from black holes, became a concrete equation. Space-time curvature, gravitational forces, even black holes themselves could be reinterpreted as quantum interactions on a distant surface. Everything we perceive as volume could be an emergent illusion, a projection of data stored at the edges of the cosmos. In such a holographic reality, information never disappears because it never truly leaves the boundary. What falls into a black hole in the bulk is simultaneously encoded on the horizon, and what evaporates as Hawking radiation is merely the re-expression of that same boundary data in another form. The paradox dissolves not by saving information inside the hole, but by realizing that inside may have never been fundamental to begin with. Yet this resolution carries an unsettling implication. If the universe itself is holographic, then what we experience as space, distance, and depth may be emergent phenomena, byproducts of correlations between bits of quantum information. The very geometry of reality would not be an independent entity, but a pattern of entanglement. The fabric of space-time, in this view, is woven from information itself. Black holes thus become more than astrophysical objects. They are windows into the code that generates reality. Their paradox reveals that the universe is not built of matter and energy alone, but of meaning, measurable, calculable, yet immaterial. In solving the paradox, physics exposes its most audacious truth. The cosmos may not contain information. It may be information. If space-time is not fundamental but emergent, then something deeper must give rise to it. The most powerful clue comes from quantum entanglement, the invisible link that binds particles even when separated by light years. Entangled particles share a single quantum state. Measuring one instantly constrains the other, no matter the distance. This correlation doesn't transmit information faster than light, but it reveals that the universe's fabric is built from relationships, not locations. In the holographic view, these relationships are the geometry. Imagine every quantum bit of information, every qubit, as a node in a vast network. The degree of entanglement between nodes determines how close or far they appear in emergent space. When two regions are strongly entangled, space-time between them appears smooth and connected. When entanglement is lost, that connection weakens. Space itself seems to tear. What we call distance may be nothing more than the strength of quantum correlation. This idea, refined by physicists like Mark van Raamsdonk, turns geometry inside out. Curvature, gravity, even the structure of black holes could arise from the pattern of entanglement across quantum states. The event horizon would then be the ultimate entanglement boundary, the place where information becomes maximally scrambled, yet still encoded. Hawking radiation, far from being random, might subtly mirror the correlations of what fell in, restoring unitarity through complexity so extreme it looks like chaos. If this interpretation holds, the black hole no longer destroys information. It transforms it through quantum entanglement, weaving every fallen bit into the geometry of its horizon and eventually releasing it, infinitesimally encoded, in its radiation. The apparent destruction is simply the limit of our ability to read the pattern. Einstein once said that space is what prevents everything from happening at once. Entanglement now suggests the opposite. Space exists because everything is already connected. The black hole does not break the universe's memory. It reveals what memory truly is, a geometry of connection written into the quantum heart of reality. For a moment, it seemed the information paradox was resolved. If information is stored on the event horizon and released through subtle quantum correlations, unitarity could survive. But in 2012, a new dilemma erupted, the firewall paradox, and it reignited the conflict between quantum mechanics and general relativity. It began with a deceptively simple question: can an observer fall harmlessly through the event horizon? According to Einstein's relativity, the answer must be yes. A falling astronaut should experience nothing special at the horizon, no wall, no rupture, just a smooth continuation of space-time until the singularity. But quantum mechanics, combined with the logic of information preservation, disagrees. If the black hole's radiation is entangled with the information encoded on its surface, and that surface is also entangled with the interior, a contradiction arises. Quantum law forbids a single system from being fully entangled with two others at once, a principle known as monogamy of entanglement. To resolve this, something must break. If the entanglement between the interior and the horizon is severed, the smoothness of space-time at that boundary disappears. The horizon, instead of being a gentle crossing, would become a searing wall of high-energy quanta, a firewall. Any object attempting to enter would be instantly incinerated, destroying Einstein's vision of a continuous geometry. The firewall paradox forces an unbearable choice. Either quantum mechanics fails, allowing information to be lost, or general relativity fails, allowing space-time itself to break at the horizon. Both theories cannot be true everywhere at once, yet neither has ever been wrong. Physicists have proposed countless reconciliations. Perhaps the horizon is an illusion projected by quantum correlations. Perhaps information escapes through microscopic wormholes, connecting interior and exterior states. Each theory saves one law by bending another. None feel final. The black hole, once the universe's simplest object, has become its most complex, a place where existence itself must decide whether to remain continuous or to preserve its memory. A horizon that burns is more than a contradiction. It is the moment when reality defends its own secrets. When the firewall paradox cornered physics, some theorists looked for escape not in destruction, but in connection. If entanglement links distant particles, could it also link regions of spacetime themselves? In 2013, Juan Maldacena and Leonard Susskind proposed a stunning conjecture: ER Chars EPR. The equation bridges two seemingly separate ideas: Einstein-Rosen, ER bridges, better known as wormholes, and Einstein-Podolsky-Rosen, EPR entanglement. Their claim was audacious. Every pair of entangled particles might be connected by a microscopic wormhole. This means that quantum entanglement and space-time geometry could be two sides of the same coin. A black hole and its Hawking radiation, both quantum entangled, might remain connected by a hidden wormhole. Information doesn't need to escape the black hole by violating relativity. It could traverse this geometric thread, invisibly, instantaneously, and without breaking any physical law. What once seemed like teleportation becomes continuity. If ER re EPR is correct, then a black hole's interior is not sealed off from the outside world. Every bit of Hawking radiation is a mirror fragment of the interior, linked through the geometry of entanglement. The black hole evaporates not by erasing information, but by transferring it through an expanding web of invisible wormholes. The process is unimaginably complex, but fundamentally lawful. The paradox dissolves, not through violation, but through hidden unity. This view redefines what a black hole is. It's not a place where things end, but where connections reach their most intricate form. The singularity may not be an abyss, but a knot, a convergence of all paths where space-time folds information back upon itself. Hawking radiation, then, is not random noise. It is the slow unbraiding of that knot, the universe whispering back what it once consumed, syllable by syllable of quantum code. If the universe is holographic and connected through entanglement, then perhaps wormholes aren't exotic tunnels through distant galaxies. They are the fundamental threads that weave reality together. The black hole no longer hides meaning. It is the meaning, folded so tightly that only geometry can remember how to read it. Every attempt to resolve the information paradox leads to the same unyielding demand. Unitarity must hold. No matter how chaotic a process appears, the sum of all possible quantum outcomes must always equal one. Nothing, not light, not matter, not meaning, can vanish from the cosmic account. Even black holes, those perfect engines of disappearance, must obey this rule. But how does the universe ensure it? Recent progress has turned speculation into precision. Using quantum information theory and powerful computational tools, physicists have begun to reproduce the full life cycle of black holes in simplified toy models. These simulations, especially those based on random quantum circuits and page curves, reveal something astonishing. As a black hole radiates, the entropy of its radiation first rises, as information becomes increasingly scrambled, but then falls again as correlations begin to leak out. This curve perfectly matches what unitarity demands. Information does escape, just not as recognizable data, but as structure hidden in quantum correlations between the emitted particles. To an external observer, the radiation appears thermal and random, yet beneath that randomness lies order, a deeply encrypted record of everything that ever crossed the horizon. Hawking's original calculation missed this subtlety because it treated the radiation as independent emissions. In reality, the radiation is entangled with itself, with the horizon, and with the black hole's remaining mass. When the whole finally evaporates, the total system remains pure. Nothing was ever lost, it was only disguised. The implications are profound. Unitarity doesn't merely describe the conservation of probability, it describes the conservation of meaning. The universe does not delete, it transforms. Every event, from the birth of a star to the death of a black hole, becomes part of a continuous informational flow that cannot be broken, only reinterpreted. In this light, black holes are not paradoxes to be feared, but proof that reality is more consistent than our intuition. The universe, at its deepest level, is a perfect accountant, a machine that records every quantum whisper and balances its books with infinite precision. The cosmos remembers, not because it chooses to, but because forgetting is impossible. At first, the black holes seem to represent a fracture in reality, a place where Einstein's smooth geometry and quantum mechanics' rigid logic tore each other apart. Yet after half a century of debate, a strange reconciliation is emerging. The paradox was never about destruction, but about perspective. Relativity and quantum theory describe the same event from opposite sides of the horizon, and both can be true, if reality itself is relational. From the viewpoint of an outside observer, information never crosses the horizon at all. As an object approaches, time slows to a crawl, and its image freezes on the surface, gradually redshifting and fading into invisibility. To this observer, the horizon is where all information remains, an eternal film stretched over the edge of space-time. But for the infalling observer, nothing special occurs. They pass smoothly through the horizon, carrying the same information inward. Both descriptions are valid within their own frames. The contradiction arises only when we demand a single, absolute story. Quantum mechanics already forbids such absolutes. Measurement, observation, and entanglement all depend on context. What the black hole forces us to see is that space-time itself may share this relational nature. The universe does not contain one objective history. It contains a network of overlapping perspectives, all consistent within their own domains, all stitched together by information that never ceases to exist. This convergence suggests that the boundary between geometry and information, between gravity and quantum theory, is not a line to be crossed but a symmetry to be recognized. Space may emerge from entanglement, time may arise from the flow of correlations. Reality, in the end, is not made of things but of relationships, patterns stable enough to appear solid. The black hole's paradox dissolves not by choosing a side, but by revealing that both sides were projections of the same deeper law, that existence is self-consistent even when its languages seem to contradict. The universe, seen rightly, is the reconciliation of its own impossibility. In the end, the black hole does not erase reality, it completes it. What once appeared as destruction now reveals itself as transformation, a perfect cycle in which information is never lost, only translated between forms we do not yet fully understand. Matter becomes energy, energy becomes geometry, geometry becomes information, and information, somehow, becomes the memory of the universe itself. When the last Hawking photon escapes a dying black hole, it carries not a fragment of chaos, but a signature, a final echo of everything that once fell inside. Decoded across eternity, that radiation would tell the story of stars, planets, atoms, and thoughts, all merged into a single encrypted continuum. The black hole's silence was never emptiness. It was compression beyond comprehension. In this light, the paradox was a mirror. It showed us that the boundaries we draw, inside and outside, Observer and observed, existence and oblivion, are not separations, but translations. The universe preserves information because it is information, endlessly recombining its own record into new expressions of order and awareness. A black hole should have been a void, yet it became the most precise reflection of reality's logic. It taught physics that nothing can truly vanish, and philosophy that nothing can truly stand alone. Even the darkest region of space participates in the same eternal conversation, the cosmos remembering itself. When the universe looks into a black hole, it is not seeing an absence. It is reading its own source code. Write in the comments, "I still exist in the version that remembers."